So we're going to begin on chapter 4 now, which is elementary number theory and methods of proof. And we're going to start with direct proof and counterexamples. Both discovery and proof are integral parts of problem solving. When you think you have discovered a certain statement is true, try to figure out why it is true. If you succeed, you will know that your discovery is genuine. Even if you fail, the process of trying will give you an insight into the nature of the problem and may lead you to discover that the statement is false. For complex problems, the interplay between discovery and proof is not reserved to the end of the problem-solving process, but rather is an important part of each step. Some things that we're going to assume in this chapter, and well, this text in general, basically familiar with the laws of basic algebra. 3 properties of equality. Let's see here. Three properties of equality. A equals A in all instances in an equation. Okay? If A equals B, then B equals A. And also, and the third one is if A equals B and B equals C, then A equals C. Some basic assumptions. Principle of substitution for all objects A and B. If A equals B, then you can substitute B wherever you have A. We assume also that there is no integer between 0 and 1, and that the set of all integers is closed under addition, subtraction, and multiplication. That means addition, subtraction, and multiplication of integers yields an integer as well. Notice I did not include division in this, because you divide 2 integers, you can get a non-integer rational number. Even, odd, and prime composite integers. Even. An integer is even if and only if k equals 2n, where even k, if and only if k is and n is an integer. K is odd if and only if k equals 2n plus 1. N is an integer. So is 0 even or odd? Yes. It is even. If a and b are integers, six a squared b odd or even? Six a squared b, is that even or odd? Why is it a guess, not a fact? Why not a statement? Why would you say it's even?
Of equals 2 times n, 6 is number, assuming it works the same way.
Well, because multiplication is closed to integers, you could rewrite this as being 2 times 3a squared b. And since integers are closed to multiplication, this here is an integer. Therefore, it's 2 times some integer. Therefore, it's even. Okay? How about 10a plus 8b plus 1? Odd, because you can factor out a 2 from this and make it 2 5a plus 4b plus 1, and this is an integer. A little bit more abstract, but is every integer either odd or even? It doesn't get into the proof of that, but let's see here. What does it say? Yes, every integer is either even or odd. However, the reason for this fact is not immediately apparent. It can be deduced using the method of proof by contradiction. It is also a consequence of the quotient remainder theorem. So that's all it says as to the proof as to why all numbers are either even or odd. Let's see here. Scroll. Okay. Definition. Let me get this. Let's see if I can get this right here. N, an integer n is prime if for all positive if and only if n is greater than 1 and for, how is this worded here? All positive integers R and S R and S n equals RS and n equals R or n equals S. If yeah, an integer is composite if and this is yeah, integer n is composite if and only if n is greater than 1 and n equals RS and R is greater than 1 but less than n and S is greater than 1 but less than n. For some integers R and S. So simply put, more symbolically put, we'll put this in more formal terms here. Let's see here. N is prime. If and only if. For all integers R and S, if n equals RS, then N equals R, or N equals S. N is composite. If and only if there exists integers R and S such that N equals R, S, and R is between 1 and N, and 1 S. So that's what symbolically the two definitions are. Basically, a prime number has two integer factors, one and positive integer factors, one and the number and n, and a composite can be a multiplication of two integers other than 1 and n. Let's see here. Is 1 prime? No, it has to be greater. A prime number has to be greater than one. Is every integer greater than 1 either prime or composite? Yeah. What are the first six prime numbers?
1, 3, 5.
No, 2, 3. That's 6, right? Yeah. And the first 6 composite numbers? No, 4, 6, 8, 9, 10, 12. Oops, that's not 12. Yeah. All right. Yeah. There's another number thing. A prime number is either 6k plus 1 or 6k plus 5. Not all numbers that fall into this pattern are primes, but for each k you have, for each integer k, you have a prime number. So 6k, 6 times 1 plus 1 is 7. 6 times 1 plus 5 is 11. 6 times 2 plus 1 is 13. But notice 6 times 5 plus 5 is 35, which is divisible by 5 and 7. So it's not a prime. But a quick and dirty way to check to see if a number is prime is to see if it falls into one of these two categories. The proof on that, I have no idea. I imagine it's rather complex, but read that one somewhere. Okay, let's see here. Proving existential statements. Okay. So according to the definition, a statement in the form of there exists some x, which is an element of D such that Q of x is true. If and only if Q of x is true for at least one element of D x. One way to prove this is to find an x in D that makes Q of x true. Another way is to give a set of directions for finding such an x. Both of these methods are called constructive proofs of existence. So there exists an x in D such that Q of x is true. Method 1, find an x in D that makes Q of x true. Second way, give instructions. For number 1, for finding that. And these are constructive proofs of existence. Yeah. E. All right. Another term for that is the local principle underlying such a proof is called existential generalization. It says that if you know a certain property is true for a particular object, then you may conclude that there exists an object for which the property is true. So if it's true for one, then obviously there exists an object for which the property is true. Existential generalization. All right, let's see here. Prove let's see here. Prove there exists an element of Z such that N equals prime 1 and plus prime 2. So find an integer, in two ways. N equals prime 3 plus prime 4. Prove that such an integer exists. Well, easiest way to do it would be to find one. So just experiment around with different prime numbers and see what works. So let's say n equals 5 plus 7, or 5 plus 5. And n equals 7 plus 3. So there you go. There's an example. So it proves that that this statement is true. There are two ways to do it. How about suppose that R and S are integers. Prove that there exists an integer k such that 22R plus 18S equals 2k. Well, solve for k and substitute any two integers. Solve for k and then substitute two integers in for R and S, and you get a k. It's just a matter of substitution and that sort of thing. So that one you would do by giving directions on how to do it. So you solve for k, and then k is an integer because it is the sum of products of integers, and by substitution and the distributive law of algebra, you can solve for k. Thus, there exists an integer, namely k, such that 22r plus 18s equals 2k. You don't have to come up with an example. You can just give directions on how to solve it. All right, a non-constructive proof of existence involves showing either A, that the existence of a value of x makes q of x true is guaranteed by an axiom or previously proved theorem, or B, by the assumption that there is no such x leads to a contradiction. The disadvantage of a non-constructive proof is that it may give virtually no clue about where or how x may be found. The widespread use of digital computers in recent years has led to some dissatisfaction with this aspect of non-constructive proofs and to increased efforts to produce constructive proofs containing directions for computer calculation of the quantity in question. Disproving. universal statements by counterexample. It's actually supposed to be one word, but whatever. To disprove a statement in the form A of X, there exists, well, let me just write it. For all X in D, if P of X, then Q of X. To disprove it, find a value of X in D for which the hypothesis P of X is true and the conclusion Q of X is false. Such a X is called a counterexample. So find an X element of D such that P of X and not Q of X. X would then be the counterexample. Let's see here. Disprove the following statement by finding a counterexample. For all real numbers A and B, if A squared equals B squared, then A equals B. Counterexample for that? If A squared equals B squared, A equals B for all real numbers. What would an example of that being wrong be? Yeah, but what would the counterexample be? Minus 1 and 1. Minus 1 squared equals 1 squared, but A and B, but minus 1 does not equal 1. So minus 1 would be a counterexample. So now proving universal statements. Now, the method of exhaustion is using every element in the domain and putting it into the predicates involved and showing that it holds true for all elements in the domain. So, if you had the statement for all n elements, all n integers, if n is even and n is between less than or equal to 4, or greater than or equal to 4, but less than or equal to 26, then n can be written as a sum of two prime numbers. You would take all the even integers between 4 and 26 inclusive and show that they can be written as the sum of two prime numbers. It would be exhaustive and maybe a little bit exhausting, but it is possible. They do it in the slides. I won't do it on the board here, but that is the exhaustive proof. Let me put that up here. Show it is true for all elements in domain. The most powerful technique for proving a universal statement is one that works regardless of the size of the domain over which the statement is quantified. So if the domain is an infinite set, you can't do an exhaustive proof. You can't do infinite number of examples. It is based on the logical principle called universal generalization. All right. Let's see here. To show that every element of a set satisfies a certain property, suppose X is a particular but arbitrarily chosen element of the set and show that X satisfies that property. So let's see if we can come up with an example here. At some time you may have been shown a mathematical trick like the following. You ask a person to pick any number, add 5, multiply by 4, subtract 6, divide by 2, and subtract twice the original number. Then you astound the person by announcing that their final result was 7. How does the trick work? Give the variable x for the original number. And then you go through the various algebraic steps and then show that the result, regardless of the original x, is 7. It is shown on slide 31 of chapter 4, section 1, if you would like to see it. Even if I put it up on the board, it would be kind of small. So the process drawn out. You can generalize from the generic particular to conclude that if you follow the steps, you will always get 7, regardless of the initial value that you put in place of x. When the method of generalizing from the generic particular is applied to a property of the form if p of x then q of x, the result method is called a direct proof. So, method of direct proof. Let's go through the steps here. All right, step 1. Express the statement to be proved in the form of for all x in D, if P of x, then D of x, Q of x. All right. You express it in that form. Yeah, in symbolic form. Start the proof by supposing x is a particular but arbitrarily chosen element of D for which the hypothesis P of x is true. So you suppose x is an element of D and P of x. And then show that Q of x is true using definitions, previously established results, and the rules for logical inference, which we've covered before. So just as a simple example, prove this, that the sum of any two even integers is even. So for all x and y, elements of Z, if x and y are even, then x plus y is even. So you pick x and y. Okay, x equals 2k by the definition of even integers, right? Y equals 2m, again, from the and k is an integer and m is an integer by the definition of even integers. So x plus y would then be equal to 2k plus 2m, and that's equal to 2 times the quantity k plus m, and n is an integer, because addition is closed to integers, so n is an integer. So x plus y equals 2 times some integer and is therefore even. So there you go. The sum of two even integers is even. Whenever you are presented with a statement to be proved, it is a good idea to ask yourself whether you believe it to be true. In this case, you might imagine some pairs of even integers, such as 2 plus 4, 6 plus 10, etc., and mentally check that their sums are even. But since you cannot possibly check all pairs of even numbers, because the set of integers is even integers is infinite, you cannot know for sure that the statement is true in general by checking the truth in these particular instances. So, let's see here. So you first do the formal restatement for all integers x and y. If x and y are even, then x plus y is even. Next, ask yourself, how should I start the proof? What am I supposing? The answer to such question gives you a starting point or first sentence of the proof. Suppose x and y are even integers. Then ask yourself, what conclusion do you need to show in order to complete the proof? M plus n is even. Since both involve the term even integer, you must use the definition of this term, and thus you must know what it means for an integer to be even. Okay. One of the basic laws of logic, called existential instantiation, says, in effect, that if you know something exists, you can give it a name. However, you cannot use the same name to refer to two different things, both of which are currently under discussion. So you can call something even, but you can't call something else even as well. That's defined differently. Let's see here. Yeah, the formal definition is, if the existence of a certain kind of object is assumed or has been deduced, then it can be given a name, as long as that name is not currently being used to refer to something else in the same discussion. Let's see here. So, sum of two even integers is even. Getting proofs started. And it jumps around a little bit. Believe it or not, once you understand the idea of generalizing from the generic particular and the method of direct proof, you can write the beginnings of proofs even for theorems you do not understand. The reason is that the starting point and what is to be shown in a proof depend only on the linguistic form of the statement to be proved and not on the content of the statement. So, write the first sentence of a proof, starting point, and last sentence of a proof, conclusion, for the following statement. For every complete bipartite graph is connected. Let's see here. It is helpful to rewrite the statement formally using a quantifier and variable. So all graphs if G is bipartite, then G is connected. Is that what it said? Yeah. The first sentence or starting point of a proof supposes the existence of an object in the domain that satisfies the hypothesis of the if-then part of the statement. The conclusion to be shown is just the conclusion of the if-then part of the statement. So G is connected would be the conclusion. Proof. Suppose G is a particular but arbitrarily chosen graph such that G is complete bipartite. And then you go on until, therefore, G is connected. Fill in the blanks in the proof for the following theorem. Let's see here. For all integers R and S, if R is even and S is odd, then 3R plus 2S is even. So, let's see here. Suppose R and S are integers. R is even. S is odd. Then 3S, what is it? 3S plus 2R? No, 3R plus 2S. 3R plus 2S is even. All right, so what would the theorem to be proven? What would the first the first statement be? Suppose R is even. S is an odd integer. And then must show that show that 3R plus 2S is even. Now, a little discussed, and not even in this book or the slides does it discuss problem solving and an approach to problem solving, which involves starting from the end. What do you need to know? What do you can, because you're given the endpoint that you desire, you can work from that backwards toward what you have at the beginning. So, show that 3R plus 2S is even. So, show that, what do you need to do for that? You need to show that 3r plus 2s equals 2k. Okay? That's working back from the end, not from here. Okay? What do you know? And what do you know here? You know that r equals 2m because r is even, and s equals 2n plus 1 because s is odd. So you can work from both directions. Work with what you're starting with here and work backwards from what you want from there. So substitute, and this might give you a clue about how to proceed. Stepping back to this can give you a idea of how to proceed from here to here. See, does that make sense about working backwards from the end? In real world situations, most of the time you are given a endpoint that you are trying to reach. In solving the problem, you can work backwards from that desired outcome toward what you have to begin with. But anyway, you can go through as an exercise for yourselves, the intervening steps between these 2 points. But you can see how it works from both ends, meet in the middle, and you have your proof. That section took a little bit longer than I was expecting, so I guess next time we will do move on to section 2 of chapter 4. I guess that'll be about it for the day. Have a good day.